This is a brief walkthrough to show you how to use Excel to run multiple regressions for a simple example that deals with a data set with 20 data points. Sample size is 20, and also how to interpret the results reported after you run the multiple regressions. So in this case, we have a sample size of 20 patients or 20, let's say, person, and then the first column is the first independent variable or input age. The second one is the blood pressure. The third one is whether the person is a smoker or not. And the dependent or output variable that we are trying to estimate or predict is the probability of having strokes in the next 10 years multiplied by 100. So when you see, for example, 19, that means the probability is 0.19. Okay, so now that everything is ready, the first row is the label row and the next 20 rows are the data rows. So what we need to do is just we go to Data tab and we select Data Analysis, and then we select Regression among the menu items that shows up. So then we click OK. Now we have the input Y range. Y means output, the dependent variable. I already selected it. So effectively it is just the range that correspond to column D, starting from row 1 to row 21, as you can see here. And input X range is effectively these three. So let me reselect it. So it is starting from here, and all the three columns in this case, because I have three independent variable, one of them be the column C is a categorical independent variable because it is either yes or no, which I change to 1 and 0. 1 means it says the person is a smoker, 0 means not a smoker. And on the label side, I want to indicate that the first row is labels, and I want the confidence level for 99% to be reported, so these two are check marked. Then output range, let's say I want the results to be reported in this cell, not a new worksheet. And then residual, let's say I want standardized residuals to be reported as well as the residual plots and line fit plot. That's about it. Click OK. So things show up as you can see. Okay, so let's first deal with summary and then analysis of variance, ANOVA, and then finally residual outputs. Okay, or maybe actually starting from coefficients, maybe that's even better. So we have the y-intercept, negative 90.84. We have the b1 corresponding that is the parameter or coefficient or slope corresponding to age. We have b2, this 0.24.6 corresponding to blood pressure, and e3, the slope or coefficient or parameter corresponding to smoker, that's x3. So what I'm trying to say is, let's say this is x1, and let's say this is x2. Okay, let's move it here. So okay, so this is x2, the blood pressure. Okay, and let's say this is x3, so that's my third independent or input variable. Okay, so effectively we can say that our regression is y, or the output y hat, is equal to, so what I have is negative 90.8451, let's say keeping three significant digits, plus 1.076 times, so that is times x1. And after that we have 0.246 times x2. Let's keep this clean. So this is x1, and let's this not capital Y. Okay, and then we have plus 9.1306 times x3. So that is our estimated regression equation for this three variable multiple regression run. Okay, so we have that. That's good. Now we need to also keeping here is the standard error. Basically, this is the standard deviation of error associated with B1, which is this value, and B2 and B3. So this is SB1, this is SB2, and this is SB3, standard error. We will use them because T stat is effectively the B1 divided by SB1 that you get here. And 0.246, that is B2 divided by corresponding SB2, give you this. And finally, 9.13 divided by 3.01 gives you 3.024, which is the third T stat for the smoker. That's the statistic that we're going to use. And then p-value is the corresponding significance probability for this t value. So t-value of negative 5.9 has a significance of 2.21 e to the negative 5. Okay, so before getting to the rest of this, because rest of it is just effectively the lower and upper bounds for the confidence interval, and then lower, that's for 95% that by default Excel reports. For example, it says the 95% lower and upper bound confidence interval for, say, the B1, which has a mean value of 1.076, is this range, 0.71 to 1.434. And also lower or upper bound for confidence interval for, let's say, B2 is this range. And you can see that lower and upper bound confidence interval for B3 is this range. 99% confidence interval, of course, is much wider. And you can see, I mean, for B1, the lower and upper, for B2, lower and upper, and B3, lower and upper. Okay, so what is the rest of information here? We have R squared, which is the multiple coefficients of determination. And it's basically saying 87.3% roughly of the information associated with stroke probability or the variability associated with the stroke probability as reported here is already captured by this estimated regression equation and the coefficients that we found. So, but better than R square is adjusted R square. So that's the one we would like to use because it normalize or it compensate for the fact that we have 3 independent variable, because the more independent variable you add to this equation, even if they are useless, R square will increase even slightly. But adjusted R square tries to compensate for that so that simply adding not relevant independent variable to the equation would not just increase adjusted R square. So you can see that it's less than R square. It means 84.9% of the variability in what we are trying to predict is already captured by our regression model. So that's not bad. That's about 85% of information captured. Okay, we have 20 observations, so that's n equal to 20. That's the sample size. Now here we have regression, residual, or basically the error, because in our model we have always an error, which is usually shown like this. So we have an error term, epsilon, and this error term is the one that it's the error term for our regression model, and the standard deviation for that is reported here. I'm going to show you, but this residual error and this total and degree of freedom for regression is 3 because we have 3 independent variables, x1, x2, x3. Regression has 16, and that is because the n equal to 20, so 20 minus 3 minus 1. So that's 20 minus 4, so give you 16. And then total degree of freedom is just 20 minus 1, and that gives you 19. So these are degree of freedom, and then sum of squares due to regression. So basically the number you see here, let me just clean it up. So let's just keep it this. Keep 3,671. So effectively what this is SSR. So it is sum of square due to regression. So Let's remember that. Okay, and well, I can write it here. SSR is equal to 3671, and then SSE, sum of squares due to error, is what is reported here, which is 534. Let's say 35 to be accurate. We round up. So it's 535. And then the SST is the sum of these two numbers. So SST is SSR plus SSE. And if we sum these two numbers up, we get to 4206. Okay, and so mean square, let's say, so we have mean square due to regression. And that is effectively this number divided by corresponding degree of freedom. So you can try it. So let's say I can write it here. So let's just write in front here. So I'm going to write MSR, mean square due to regression, is equal to, and I'm going to keep it this way, and is equal to sum of a square due to regression SSR divided by degree of freedom. You can see this number is equal to what is reported here. So that is correct. And then you can also say MSE, sum of a square due to error, and that number is equal to sum of a square SSE divided by the corresponding degree of freedom. So you can see it's 33.43, roughly this number as reported. Okay, and F, our F test statistic, is just simply F is equal to MSR divided by MSE. So ideally, in ideal world, there is no error associated with the regression, and SSE and also MSE are both zero. Therefore, denominator here should be ideally zero, which means ideally the F value should be infinity. But in practice, that's impossible. We always have some error. So SSE is not zero, MSE is not zero. But that is giving you the message that, or the signal that F supposed to be in a good regression, supposed to be a large value. For example, in this case, 36.6. And if you compute that, so it's basically this number, MSR, divided by this number, MSE, and it's 36.61. That is similar to this number here. Significance of F with this p-value. So I can replace this by just saying p-value. And that is the probability associated with F. It is already automatically computed by the engine, regression engine. But if you're interested to see where it is coming from, it's effectively using the F. Since we are trying to find a probability, you're using F distribution and right-sided, right tail. RT means right tail, F distribution. As you can see, there are three arguments. X is the value, so that's the statistic we found. The degree of freedom is the degree of freedom associated with numerator for F. That's the statistic, which is MSR, and MSR has a degree of freedom of 3, so 3. And then last argument, the second degree of freedom is associated with the denominator in F formula, MSE, and MSE or SSE has a degree of freedom 16, so 16. See, the value that is reported is exactly what the engine found. So what I'm going to do is, as a reference, I am going to keep it here. This is the function that is used effectively if you're using Excel function. Okay, so that's about that. Multiple R is the um, uh, correlation coefficient, and the way you find it is just you take a square root of the R square. There you go, 0.9. So this value is the correlation coefficient. I'm going to write it here. And effectively, it's just a square root of R square. And standard error is just a square root of MSE. So take a square root of MSE, and that gives you exactly the standard error. So I am going to keep the formula here. That is the standard error for the error term in the regression. And okay, so we completely analyzed and discussed the summary output, the meaning of the terms in the summary output, the meaning of the components in the ANOVA, which is analysis of variance. The last thing here is we already talked about the coefficient, the standard error associated with them, the t-stat, and the p-value. P-value, especially these three values here. If you're interested how these are computed, you can just use Excel function because we are trying to find a probability. We need to find t-distribution, and it's a two-tailed. So you need to use 2t, which means two-tailed or double-tailed, right and left together. There are two arguments, x. For example, if I want to find here, this is corresponding to t-value 6.37, so that's the first argument. The degree of freedom is always the degree of freedom of error, which is 16 in this case, so 16. And you can see this number matching that. So I am going to keep it as well like that. You use the two-tailed t-distribution to find these numbers. Okay, and we talked about therefore all these numbers. Lastly, residual output. These are the 20 observations we have, and these are the stroke probability times 100 that are computed by just feeding these three value for x1, x2, x3, or substituting these three values for x1, x2, x3 into the regression equation, and you will end up finding this value, and then you subtract this value from what is the actual observation, and the delta, meaning 19 minus 17.27, is this residual. Absolute value of residual, not much informative, but then when you go with the standardized or standard residuals that is automatically computed, these values are the ones we care about. So these values, you just need to double check that whether there is anything above 2 or below negative 2.4. And as you can see, everything is okay except for one value here, which is less than negative 2. So what I said is just watch for values that, let me just use a red color. So watch for values that are either above 2 for standard residuals or below less than negative 2, and this value is. So this is probably an outlier, maybe an outlier. So this needs further investigation, basically. This data point 11, which is this data point, I would say it worth investigating this data point. And by investigating, I mean it worth going back, first make sure that whatever and whoever was involved in capturing this data, it was properly captured. There was no, if the sensor was involved, that sensor was properly applied. There was no mistake in taking the data. If that is confirmed that this is a real data, then we need to go back and maybe rerun the regression temporarily, omitting and deleting this data temporarily. And then we rerun the analysis, we find the coefficients, and we see how different these coefficients are, basically a sensitivity analysis. And if there is a considerable difference, then we need to be very careful because we need to evaluate whether we have the right independent variables in this model or not. Last point about the plots. So about the plots. Okay, so we have, what do we have here? We have the age line fit, we have the blood pressure line fit, we have the smoker line fit, we have residual for smoker, and we have residual plot for blood pressure and residual for age. Of course, these residuals are plotted against or for x-axis being the specific input variable. For multiple regression, these are not necessarily useful. Usually, if somebody is interested in plotting the residual, they want to plot the standardized residual versus the y-hat. So we can do that if we can basically do this, plot these two things. and we can go to, say, data, or say insert, and then we can do a scatter plot if I can find it. Oh, there you go. This is a scatter plot. Okay, good, not bad, not this for sure. Let's say this is scatter plot. So this is what is usually useful for, um, let's say, for regression analysis. This is scatter plot. You can always massage the plot because there are different versions of it that you can plot, like this one. The nice thing about this scatter plot is when you plot the residual, or basically the standard residual, against the y hat, then you can see that it's relatively good pattern of residuals. There's not a bad pattern here. So that's the last point that worth discussing. But this is I would say, an introductory review of how you can run multiple regression with Excel and how you can translate or interpret the results.